Eric Rule is a member of the technical staff in the Mobile Solutions Business Unit at Maxim Integrated. He's responsible for validation and debug, evaluation hardware and software development, and design in solutions for design and support. Eric has a BS in electrical engineering from the California Polytechnic State University in San Luis Obispo. All right, I will go ahead and start the webinar.
Good morning, everybody. Thank you, Monica, for introducing me. As she said, my name is Eric Rule, and I'm an applications engineer in the Mobile Power Business Unit at Maxim Integrated. And today I'm here to present to you basically one of our power supplies and how you can use it when you're designing with an FPGA. So the product in question is the MAX 77812. It's a quad phase configurable buck regulator. If you don't know what multi-phase regulators are, I'll tell you about that in a moment. So kind of the overall agenda for today, I want to talk about, just give you a brief overview of the product, some of the specs, the input-output specs, things like that, talk about some of the features. Once we kind of go over the product itself, we'll get into what I think of as creating a schematic or drafting a design. So the way I've structured the presentation is, if I was designing this into a system with an FPGA, how would I go about doing that? So we're going to start with understanding your FPGA requirements. We'll talk about how to configure the input of the IC. We'll talk about how to configure the output and the phase configuration, and then some of the extra features like communications, sequencing, and DVS. And then I'm going to briefly talk about Maxim's online simulation tool, EESIM. It's a free online web tool. You can use it to create a design and simulate it. We don't have time today to go through a full start to finish EESIM exercise, but it's a pretty intuitive software, so you should be able to figure it out relatively easily, and there's some help there on the website. So once we get through that, we'll talk about layout, which is actually implementing your design onto a real board. I'll go over some of the best practices that we recommend, and I'll offer up some resources that you can use for assistance. And then I'll briefly mention how to choose a version of the part, and we'll finish off with some closing remarks, and we'll get to Q&A at the end. So before we get into it, let's just talk a little bit about FPGAs in general. So when you design with an FPGA, you use it because basically it makes the design process overall quicker. Due to the nature of the programmability and the reconfigurability of the FPGA, your design cycle, as the requirements change throughout the process, maybe things come up in the market and you have to change your design to adapt. FPGAs really enable you to change those things on the fly quickly. And they're high performance devices, so you can do a lot of different things with them. And there are many different challenges that come with designing with an FPGA. Today specifically, I'm going to be addressing the power challenges. So designing your power delivery from your source to your FPGA. So in that realm, FPGAs have a lot of different rails. There's some sequencing restrictions that need to be met. Definitely, you're going to want to make sure that your efficiency is optimized primarily for heat distribution. And then we'll talk about, in layout, how to make sure that we keep things compact to keep the power density high. So it leaves you board space to do other things. So typically when engineers design with FPGAs for power stages, you're going to run into two different approaches. One is designing with discrete integrated circuits, which is what we're going to be talking about today. And that's picking out different PMICs or regulators and putting them on the board individually, laying them out, and creating your design that way. there are things in industry that sometimes are called modules or bricks that are essentially multiple discrete power integrated circuits combined into a single package on a single substrate. And typically they'll actually place the necessary passive components on that substrate. So what it means for you is the layout work is done. So that definitely makes using modules easy, because you just drag and drop the module onto your board. It's easier to lay out, and it keeps your BOM down. However, generally you're going to find that these are a lot more expensive, because you're paying not only for the circuitry, but you're paying for the work that went into packaging all that into a nice solution. And they're going to be impossible to debug if you run into issues, because you can't open up the module and change components and probe. And you're definitely gonna run into, I think, a more challenging thermal profile when you use these modules. Now, what we're talking about today, using discretes, they are going to require more design work, because you have to design the schematic, you have to lay it out. You're going to have a lot more components, so your BOM size is going to grow. However, it's going to use up less board space with the right layout techniques. You're going to have better performance, most likely, and the whole solution is going to be cheaper. And most importantly, it makes it so your design is flexible. So as you're working through your design process, it's easy to drag and drop different parts and different components to fix things throughout the process. So like I said, we're talking about discrete solutions. So I have a little diagram over here. Just a note, I'm going to be using the word FPGA, and I'll be talking about FPGA specifically throughout the presentation, but things like SoC, system on chips, or like any kind of applications processor that has similar power requirements, the principles that I'll be talking about here should translate to those kinds of designs as well. So in this diagram, I have an SoC here, but the point is I'm illustrating that we have a few different discrete integrated circuits that are used to power that SoC. So how does the 77812 fit into this kind of power design? Well, FPGAs typically have a lot of different rails, depending on the complexity of the model that you're using. They can be 8 rails, 10 rails, 12 rails. So these rails are going to come with a range of voltages, and 77812 specifically is suited for low voltage, we call them core rails sometimes, that require high current and generate aggressive load transient events on the power supply. So that's where the 77812 is going to fit the most. As a note, there are other rails that generally have lower current requirements and higher voltage levels. So you might consider using, Maxim does offer a lot of high performance PMICs, and you might consider using one of those as a supplementary power IC and using the 77812 as the core power IC. That's typically how these things are designed. So we're going to be focusing in on these rails that I mentioned that have low voltages and high current requirements, and how the 77812 can power them and make your design more efficient. So it's a multi-phase buck regulator. I'll talk a bit about what that actually means if you're unfamiliar in a moment, but just know that what it means is you can change the number of phases and how they're hooked up on the fly, basically. So as your FPGA design goes along in the process, you don't know your power requirements until you synthesize the VHDL that defines the architecture for the FPGA. So once you do that synthesis, then the current requirements for the power arise from that. So the good thing about having a phase configurable device is that as those design requirements changes, maybe your synthesis changes, instead of having to oh man, this power regulator doesn't work for these rails anymore. I got to pick it up, find a new one, and put it in. The 77812 simply requires you to change, make a quick schematic change to change the phase configuration to match whatever your new requirements are. Definitely makes the process easier due to its flexibility of configuration. So that's kind of where 77812 fits into these designs. So let's just go over some of the basics of the part to give you a better feel of the product as a whole. So here's a block diagram of the device. Like I said, it's a 4-channel phase configurable device. The input range is 2.5 to 5.5 volts, so it was designed for single-cell lithium-ion battery inputs. That's something to keep in mind when you're determining your source input for the whole system. We'll talk about that in a moment. The output range is very low, so it's 0.25 volts up to 1.525 volts through I2C programmable steps. And even though the defined maximum output voltage is 1.525 volts, it can go up to 2.7 volts using an external resistor divider. So you basically would inject a resistor divider onto the feedback network to increase the output voltage. And Maxim has an application note that describes that whole process for you. So if it's something that you end up wanting to utilize, there's some resources for you to figure that out. So each phase can supply up to 5 amps of total output current, steady state. So if you have a single phase, it can do 5 amps. You combine it with, you have 2 phases, that's 10 amps, 3 phases, 15 amps, 4, 20. So if you have all 4 phases combined into one, you can have one output that has 20 amp capability. It also has dynamic voltage scaling. So that's what we call DPS for short. And it's something that is pretty critical for FPGA applications. So we're going to mention this a bit later, and it's something you're probably going to want to utilize in your design. It has programmable sequencing, so you can, with I2C, program these registers very simply to set the sequencing up and down for your regulators as they enable and as they disable. In the same vein, we have programmable ramp up and down slew rates for those startup and shutdown waveforms. So there is an enable pin, like a global enable pin. We'll talk a bit more about the nuances of enabling device as we go forward, but there's a global enable pin, and there's actually a pin that we call CE here. It's called chip enable. Chip enable is something used to pre-program the device, and I'll talk more about that as we keep going. It has 2 configurable GPIs, general purpose inputs. These are only inputs, they are not GPIOs, and they serve a few specific functions that you might find useful. This product uses a 2 megahertz constant on time quick PWM control scheme that Maxim has developed. Basically, if you're designing an application that is sensitive in the 2 megahertz band, that's something you might consider. We can talk about how to minimize noise from that when we get to layout at the end. The device does come with an I2C interface. It also supports SPI. I'm going to be focusing on I2C for this presentation, but if SPI is what your system needs, just know that we fully support the protocol as well. It also comes with some protections built in to keep your system safe from adverse conditions, such as undervoltage lockout, overcurrent protection to make sure, from if you have a short circuit somewhere, this part doesn't get damaged or anything else doesn't get damaged, and it has over temperature protection as well. So it will shut down if the temperature of the die gets too hot. It also comes with output discharge to make sure that when the device is disabled, there aren't any stray voltages left in your system. And finally, this part comes in a WLP 64-pin package. That's the one I'll be focusing on. It does have a 0.4 millimeter pitch, which is quite small. It's doable, but you're probably going to want to have access to like a high density interconnect, PCB fabrication technology. And if you don't, I'll mention something about how we can work around that. So just in case you're not familiar with what multi-phase buck regulators are, multi-phase regulators essentially split the switching of a single output. So normally you have, a set of two switches that alternate to buck down to a single output. What multi-phase does is it splits that switching of the current among multiple phases, multiple sets of switches. And in a multi-phase topology, phases are typically interleaved, and they're out of phase proportional to the number of phases that are set up and combined. So if you have two phases, they're 180 degrees out of phase. If you have three phases, 120, 4, 90 out of phase. You can see here I have a scope shot here of a 4-phase regulator switching. These are the LX nodes, and you can see that they're each about 90 degrees out of phase of each other. And as this one finishes, the first one switches again. So each phase has its own passives, its own inductor and caps, and in this case, internal switches. And multi-phase regulation provides a few key benefits. So first, it provides reduced output ripple by way of inductor current cancellation. It keeps your component size small. That's pretty important. When you split up into multiple phases, you split the inductor current into different inductors. So if you're trying to get 20 amps of output current, instead of having to have an inductor that can tolerate 20 amps of peak current, you split that among 4 inductors that can handle 5 each. Keeps your sizes small. And it can generally provide better transient response to aggressive transients because each phase has less energy stored in it, so there's less of an aggressive change when a load transient comes. And here's just like a simple diagram of what it looks like when you set this device up for different phase configurations. So there's 5 total combinations. 1 plus 1 plus 1 plus 1, which is 4 single outputs. 2 plus 1 plus 1, which is 1 combined with 2. 2 single ones. 2 plus 2, 3 plus 1, and finally all outputs connected as a 4-phase configuration. And there are 3 pins on the device that are called phase config 0, 1, and 2. That depending on how you strap them either to ground or to VSys, by this truth table determine the phase configuration that the device thinks that it's in. So that's kind of an overview of the product. Let's get into actually creating a schematic with this thing. So first, just for the whole process, this is just how I would go about designing this regulator into an FPGA system. So I'm going to start by first just going over kind of your typical FPGA power requirements. Then we're going to talk about how to set up the input, how to set up the output, get the communications up and running, figure out your sequencing, and we'll talk about DVS. So first, I think before doing anything is just to understand where you're going to fit this device into your system. So I have like a simple diagram here of an FPGA and some typical rails that come with the FPGA. So generally you're going to have a core rail, sometimes called VCC, that powers like these critical internal logic blocks. You're going to have an IO rail that powers IO buffers and IO drivers. You're going to have an auxiliary rail that supports like kind of miscellaneous functions in the FPGA, such as clock managers, things like that. And then finally, you're probably going to have a transceiver. The transceiver portion is actually comprised of a few different rails that power PLLs or transmitters or receivers, things like that. So the core rail powers the bread and butter configurable logic blocks that you use in FPGA 4. Power this block RAM that's used. They power digital signal processors, and generally it has the highest current requirement of all the rails. It usually has strict accuracy requirements and must be sequenced first up and last out in the sequence. So the 77812 definitely is a good fit for this rail because of the high current requirement, and generally it's at a low voltage, the rails that support that. So the I/O rail, again, generally a higher current rail. It's determined by the number of I/Os that you actually use in your FPGA design. Usually the current is low enough for one phase to support. The accuracy isn't crazy strict and has a lower priority. This is a good fit for 77812 as well. The auxiliary rail typically is a little bit higher of a voltage, 1.8. Like I said, the 77812 can support this voltage with the resistor divider. We have an app note for that. I would say maybe consider supplying this rail from a companion PMIC. The 77812 is probably overkill for this rail since the current is a very low requirement. And then the transceiver blocks, the voltages range. It's up to you to figure out if you want to use 77812 or not. Just a note, if there is a rail that has a low noise requirement because it's sensitive, the 77812 can be forced to operate in PWM mode at all loads, which reduces the output ripple greatly. So that, coupled with a good layout, will make sure that your noise specs are met for the transceiver rail. So you just got to ask yourself a few questions. Look at the voltage, get a rough idea for the current requirement. Like I said before, you're not really going to know until you finish synthesizing your FPGA design how much current the rail is going to require. But you can sort of guess if it's going to be in the range of amps or multiple amps. And specifically, if they're going to be aggressive load transients, it's definitely a good fit for 77812 because it is a point of load power supply. So once you kind of figure out which rails you want to power, you need to first look at your power source. So where is your power actually coming from in your system? And typically it starts from a 48 volt plane. It can be lower, like 24 or sometimes even 12 volts. But in any case, you're going to want to generate what's called an intermediate rail. And you're going to use an isolated DC to DC regulator to do this. So the thing you'll have to make a choice on is what the value for the intermediate rail is. And typical values are 12, 5, and 3 volts. Max 77812 does not work with 12 volts. You'll need to do 3 or 5 for it. But a good thing about that is, the lower the intermediate voltage rail, the better point of load efficiency, which means you're going to reduce heat on the actual critical part of the board. So once you take your power source, you generate your intermediate rail schematically, all you have to do to hook that power up to the input is to, I've highlighted here in these red boxes, first connect that rail to the sys pin, and then connect the in1, 2, and in3, 4 pins also to sys. So they're all connected to the same source. The difference is sys is a low current, pin. It doesn't consume a lot, so you'll bypass it with a small cap, usually like 1 microfarad. And then the in1, 2, and in3, 4 are the power stages. So they are going to need a little bit higher bypassing. So we recommend 22 microfarads. So that's it for the input connections, very simple. Phase configuration. Here's the table I've shown before of that truth table of the pins. One thing to know is that when you set your phase configuration pins, you can see down here in the bottom corner, there's this active control registers diagram. What this means is if you have like a multi-phase configuration, say a 4-phase, only the registers from the first phase are going to be read. All others will be ignored. So that's something to keep in mind when writing your firmware. Another thing to note is that setting these pins determines the I2C slave address, and we'll talk a little bit about that in a second. But basically, you've done the work of choosing your rail assignments based on your requirements. All you have to do is, follow this diagram here. Hook up your inductor to your LX nodes. Hook up your output cap to the other sides of those inductors. Hook up power ground to the ground side of the cap, and then you're going to want to connect your sense P and sense N. These are your feedback pins to those output caps. So the 77812 does use differential sensing. So you're going to want to make sure that each phase is connected to its local output capacitor. Even if it's in a multi-phase configuration, the slave phase and the master phase should both be connected to their output capacitors. And to make it a multi-phase configuration, all you really need to do is connect the outputs. You can see here, this trace is connecting these two. And it's as simple as that to hook up the output. Here are your phase config pins down here at the bottom, and to strap them high, just tie them to VSys. To strap them low, tie them to ground. They're high impedance inputs, so there's going to be no leakage going into them. Once we're done with configuring the output, we can just work on getting communication set up. So every system level design should have a controller that can send out whatever it is, I2C or SPI commands to the various devices on that board. Like I mentioned before, we do support both of those. I'm going to be talking about I2C here. There's a pin called I2C SPI select. Tie that thing to ground for I2C and set it to VSys for SPI, depending on which one you want to use. So however you set up your phase configuration, this table here shows you what your 7-bit slave address is for your I2C bus. There are unique addresses for each phase configuration. What that means is you can have multiple 77812s on the same I2C bus with different phase configurations, if that's what you need. Schematically, to set up I2C, you're going to want to power VIO, which is kind of like a logic level shifter power supply. Just connect that to sys. If you already have like a 1.8 volt rail somewhere else on your system, you can route that to here too. It's not a critical input. It doesn't have like noise requirements or anything. I think easiest is just tie it to sys. If you want to do otherwise, that's perfectly fine. And then you're going to want to put pull-up resistors on your SCL and SDA pins here to enable communication. There are some other features that you might want to take note of. We do have this pin here that is basically a watchdog timer feed. So there is a watchdog timer in the device that if you enable it, if you go too long without feeding that watchdog timer, the device will shut down. So if you want to use it, just take note of this pin. If you don't want to use it, it's easily disabled and you don't have to worry about it. There's also an interrupt output. It's like an active low interrupt output, open drain, so you'll need a pull-up resistor for that one as well. And what that does is sends out critical information about the device. So if there's like a short circuit event or an over temperature, you can read this interrupt with your processor, your host controller, and handle it how you want to in your system. And once you have these things all set up, you're done. You do want a small bypass cap on VIO probably. It can be tiny, like an 0201, 0402 cap, usually like 1 microfarad or something like that, just to filter high frequency noise to keep it smoother for operation. So we've set up communications. Now we can talk about, I think, like the last piece of the puzzle for setting this thing up for your system, and that's like sequencing. So FPGAs generally do have timing requirements, so you'll have to sequence the inputs and you have to sequence the outputs in strict timing slots, and I'll talk about how we can help you do that. Before I do that, though, I want to mention the general purpose inputs. So these two GPIs, there's two pins. Depending on the value of this bit field, there's one bit field for each GPI. They'll perform a different function. So the GPI functions all affect the buck regulators, and they can either be set to globally affect the bucks, which means that it will affect all 4 bucks simultaneously, or you can program them to individually affect a buck at a time. So the nice thing about this is, even though there's only 2 pins, you can have 2 dedicated GPI or GPOs, I guess, from your controller fed to these pins, and through I2C, you can change the function of these pins as you go. So your firmware can do all sorts of things as you're running your environment. So first, they can be set to enables. So they can be buck enables, either globally affect all the bucks or individually enable the bucks. Keep in mind, there's also a dedicated enable pin that will perform the exact same function as this first one here. So if that's what you want to use, then that's fine. They can be, we call it voltage selection. It's DVS. GPI is the only method for DVSing the buck outputs. So keep that in mind when you're thinking about this. And there's also a low power mode feature in the device that the GPIs can toggle. Low power mode, basically, when you enable low power mode, it reduces the supply current greatly by turning off some different blocks in the buck at the expense of performance. So if you are hit with a load transient in low power mode, it's going to look worse. So this is really used for any system that has battery inputs. If you're not using a battery input, you probably don't want to worry about this. If you are using a battery, when your system goes into a sleep state, you can use low power mode to conserve some power. So that's the GPIs. Now let's talk about enabling and sequencing. So you need to determine how you want to enable and disable the device. There are a few methods. The first method is enabling through I2C. So there's a bit that you can toggle to force it on or force it off. It's manual control, which means it doesn't use the internal sequencer built in, which is what this diagram here is highlighting. Basically, it's showing our internal sequencer. If you don't want to use I2C, you can use the hardware enable pin, and this enables all the regulators using the internal sequencer. And if that's not what you need either, like I said, you can use the GPIs to either do manual control or use the sequencer. Personally, I think the best way to enable and disable the devices with the internal sequencers is it handles everything for you. There's no room for error. And I think just toggling this enable pin is the best way. It frees up your GPIs to do other things, and you just have one I/O that goes to the enable pin to control the whole power regulator. So if you're using the internal sequencer, which I recommend for any FPGA design that has timing requirements, you're going to need to use this pretty much. So the way the sequencer works is, I zoomed in here, when you get a rising edge on that global enable, what happens is first, the first master comes up, so M1 powers up immediately upon that rising edge. And then you have these different time slices that are just I2C programmable. There's some bit fields that you can program these to. And what they do is they control the delay from M1 for the other masters to power up. So you program time 1 here, it delays M2's power up by this much. And if you're in a multi-phase configuration, you just need to take note of what master you need to look at. So if you're in a 2+2 phase config, there's going to be M1 and M3, I believe, for the sequencing. So use the registers to program these sequencing time slots. Another thing to know is that they will always disable in the reverse order that they're enabled. So if you look here, M1 is the first one on and the last one off. So you'll just need to look at your timing requirements for your FPGA and program these values based on that timing requirement. And like I said, all you're really going to need to look at is this enable pin and potentially the GPIs if you want to use them for enables. Schematically, there's nothing to do. They're high impedance inputs that you feed your digital signal to. It is worth noting that there is an 800K ohm resistor pull down on these pins. So if your output signal, your digital signal is very weak, it has a weak drive, you might run into issues. 800K is a very large resistor. You shouldn't run into issues with any reasonable component that has a digital output. Just before we move on, I want to mention a little more about this chip enable pin here. So what it does is it doesn't actually enable the bucks. When you set this high, it enables the I2C buffers so you can communicate to the chip before actually setting the enable pin high and turning the outputs on. So what that allows you to do is, if you need to set up a bunch of different things like your sequencing and your ramp rates and things like that, you can set the chip enable pin high, run your I2C script that programs the device how you want it, and then set the enable high to go from there. So once you have your sequencing and your enabling figured out, the last thing that you just need to know about is DVS. It's something that is usually pretty critical for these kind of applications. So if you don't know what DVS is, what it is adjusting the output voltage on the fly based on the requirements of the rail that it's supplying. So if you DVS the voltage up, you increase the voltage. It's called overvolting, and it basically delivers more power to the load, which means you're gonna have better performance out of your FPGA. And if you're DVSing down, you're doing what's called undervolting, which conserves power. So if you're in like a lower performance state, that's what you might do. It's really just like a power management technique. So like I said, you have to use the GPI to perform DVS, and it does have individual up and down ramp rates that are programmable with I2C. Those up and down ramp rates can be different, but they affect all of the bucks the same. So you have one up ramp rate, and if you DVS any of those bucks, it's going to rise at that ramp rate. And in the same vein, there are also registers that do the same thing for startup and shutdown ramp rates for the bucks when you're enabling and disabling. So once you have fixed your schematic, you have kind of architected your system and how you want to do your sequencing, your communications are up and running, you're good to go. I mean, that's it for the schematic. It should be a pretty quick process. Now, say we have a schematic done, oftentimes you might want to actually run a simulation on the schematic that you've generated before you actually put it onto a board and spend money getting a real board back. So I'm just going to mention eSIM briefly. Like I said, we don't have time to go through a full example, but there are resources online to help too if this isn't enough. So what you're going to want to do is you're going to want to go just Google Maxim eSIM. The link should come up. You're going to log in and you're going to click on DC to DC converters. When you click on DC to DC converters, it brings up this list of power ICs. You're going to want to click on this step down switching regulators drop down list. You're going to look through the drop down list, find 77812, and when you click on it, it'll bring up this picture here, which is a schematic of 77812. Now what you can do is in eSIM, you can adjust all sorts of design criteria like input output requirements, phase config, all those kinds of nice things. You can actually change out these components like your inductor and your capacitors with real, whatever, they're pre-populated with real components that Maxim has vetted and determined to be a good fit for the design. If you want to replace it with your own components, that's perfectly fine. You can look through the list and figure out which component you want to put in. Once you get your schematic set up, you go to the simulation tab and you can run all sorts of simulations like efficiency, transients, Bode stability analysis, startup and shutdown, things like that. Like I said, the software is pretty intuitive. There should be some resources online to help. if you get stuck. And another thing is, if you are like an experienced power engineer and you want to do your own analysis, that extends the scope that's available in ESIM. You can download the simplest model for the 77812. It's like a locked core model of the device that you can plop into simplest and then adjust the components however you like and do whatever you want with it. If you have some like interesting use cases that you'd like to test out, that's something you can do. So we've created a schematic. Let's say we've simulated it and everything's good. Let's move on to the final stage in the design process, which is layout. So how do we implement this design actually on a real board? A good layout of the device will improve pretty much all aspects of your device performance and your system performance overall. A bad layout in the same way will harm your performance and might cause issues. So if you have a good layout, you can get better efficiency, better metallization. Less squares means less I²R loss. You can get better efficiency out of it. A good layout will reduce switching noise at the load to make sure you have a nice quiet voltage for your processor. A good layout can help ensure regulator stability by minimizing the amount of parasitics that you have in your main control loop, and definitely going to give you better response to line or load transient events if you have a good layout. So I'm going to talk about some best practices, and then I'll mention these resources we have here. One thing to keep in mind here is when I'm talking about layout and some of the layout resources we have, they're using the WLP64 package that I spoke about earlier. It does have a 0.4 millimeter pitch, which does require dense interconnect technology. If you don't have access to that technology and you don't have the money to spend on that technology, we do offer a 64 bump BGA package, which is basically the same thing. It's just in a larger package, so the pitch is much wider, which makes it a lot easier to route some of the inner bumps out to places in the PCB. So let's talk about some key things to keep in mind when laying out this device. I think the best rule of thumb, like not only for power regulators, just this one, but any power regulator, but just most circuits in general, keeping the layout compact and small is just generally better. The tighter you keep everything, the less metal there is, the less parasitics, the better it's going to work. So when you're working on the layout, just keep that in mind, like throughout the whole process. When we're talking about these passive components, I have this diagram here that I pulled from the app note that is the layout guide. Here are your input caps here. Here are two local input caps. Here is your bulk input cap. These input caps here are smaller value than this one. This is your bulk. Here are your inductors, and your output capacitors are on the outside here. So we want to prioritize the input caps and the output caps because they are like key components in the main loop. So you want to keep them close to the bumps to keep the parasitics down. Definitely a good rule of thumb that is often overlooked is your top layer for your layout should be your hot loop. So all your metal on top layer should be carrying power. And then right below that, like the next layer down should be a ground flood if possible. That means that you have a very tight, short path for these high switching currents. And it keeps your efficiency high and it keeps your noise for the rest of your system down. Another thing to know is that we do have different ground pins. So there's power ground, and then there's analog ground and digital ground. They're hooked up at different points internally. You're going to want to connect those separately to avoid coupling noise from P ground onto A ground or D ground. Sense lines should be definitely routed to their closest output capacitor. You can see here, these dotted lines are the sense lines. They don't have to be short traces. They're not carrying any current, so they can be a bit longer. If you're doing a multi-phase output, you definitely want to route those to a middle point in the multi-phase output metal to make sure that the current is balanced. And finally, just like a good idea is to avoid breaking up any of the hot loop or the ground plane. It's sometimes called islanding. It's just not a good idea. Can cause problems. So it can be daunting laying out a complicated power regulator. Fortunately, we offer a ton of resources. So we do have an EV kit online that you can order that acts as basically a reference layout for the device. On top of that, on the website, there's actually the Gerber board files that you can download and just plug and play into your layout editor of choice. Saves you a lot of time. And we do have an app note online that is like a detailed document on layout. So if you are looking for advice, that's a great read. And once you get layout done, that's it. You've completed your design, and your FPGA should be powered very nicely. So the last thing I want to mention before we get to the end is part selection. So the datasheet has a full register map. There are a few settings with what are called OTP, which is one-time programmable registers. What that means is they're burned to a certain value in our factory, and their default value is fixed after that. So you can see here, the registers that have OTP are the default voltages for each of the phases and the startup delays for each of the phases. So you're sequencing your output voltages. The default values are fixed. They can always be overwritten by I2C, but they're fixed for the defaults. And what you just need to know is that we do have 4 different versions that are released right now on the data sheet. And so you can go into the data sheet, look at these versions, see if any of them match your requirements. If they don't match your requirements, consider using that chip enable, turning the chip enable high and doing a pre-programming technique that I discussed earlier. And if you have any extra questions, if none of these fit your design and you feel like you need some more help, just please contact Maxim. We'll help you out. We'll get you in the right direction. So that's it. There's a few design resources available online, like the data sheets, the app notes, the EV kit. There's like a knowledge base that Maxim offers that's basically like a frequently asked questions database. So if there's a question you have, you can look through that first, see what's already been answered. Simplest is a tool you can use, EESIM, like I mentioned. And then we do have CAD libraries for all this stuff to make your layout much easier. And that's it. We do have an EV kit giveaway, so just go ahead and click the link to register for a chance to win a free EV kit for the 77812 or the 77874, which is a very similar product that is a 4-phase fixed buck regulator. So it's fixed 4 phases and it has a better point of load performance at the cost of flexibility. And that's it. I hope you learn something, and I hope if you do choose to design with this, that your design process goes a little smoother based on this. And now I will leave this up to question and answers. And if you have been asking questions, I think I can go into the terminal here and answer some of them. So turning the chip enable high and doing a pre-programming technique that I discussed earlier. And if you have any extra questions, if none of these fit your design and you feel like you need some more help, just please contact Maxim. We'll help you out. We'll get you in the right direction. So that's it. There's a few design resources available online, like the data sheets, the app notes, the EV kit. There's like a knowledge base that Maxim offers that's basically like a frequently asked questions database. So if there's a question you have, you can look through that first, see what's already been answered. Simplest is a tool you can use, EESIM, like I mentioned. And then we do have CAD libraries for all this stuff to make your layout much easier. And that's it. We do have an EV kit giveaway, so just go ahead and click the link to register for a chance to win a free EV kit for the 77812 or the 77874, which is a very similar product that is a 4-phase fixed buck regulator. So it's fixed 4 phases and it has a better point of load performance at the cost of flexibility. And that's it. I hope you learn something, and I hope if you do choose to design with this, that your design process goes a little smoother based on this. And now I will leave this up to question and answers. Hope you guys got some information out of it. I think we have quite a few questions here actually that have just popped up. So I have a list of them here. I'm going to try to go through them one by one. So first we have Mario asks, what is a typical efficiency we can get with a low power and high power application? So typical efficiencies, since the output voltage is pretty low, with like 3.3 volts in at like peak load current. So the way it really works is peak load current is around 1 amp per phase. So the max current is 5 amps. Your peak efficiency is going to be at 1 amp for single phase. And then for 2 phase, it's going to be 2 amps. For 3 phase, 3 amps. 4 phases, 4 amps. You're going to get about 90% in a typical input output application with this device at peak loads. And then at 100 milliamps, you'll be getting around, I think, like 80 to 85%. So I don't know if this will work, but let me try to share. I don't know if everybody can see this. I have a graph here that shows efficiency over load with 0.72 and 0.82 volts here. So you can see at 100 milliamps, it's at about 86, 87%. And at peak load here, 1 to 2 amps, it's just below 90%. So we have some graphs in the data sheet that you can look at and give you an idea of what kind of efficiency you're going to get. But a good rule of thumb is around 90%. Shane asks, if I have an FPGA with or without a hardcore softcore processor and I'm using a 77812 to power the FPGA, I'll have to program the 77812 through other means. Is this what you mean by a host controller? Do I place a small micro on the board to perform this, or is this usually done through an external micro? We break out the pins. Yeah, I think typically you're going to want to have a micro on the board. If you don't want to put it on the board, breaking it out to a header of some other board is perfectly fine too. Basically, I think designing with this chip and like any modern power regulator, you're probably going to want to have I2C somewhere. And he also asks, I assume after I've programmed the chip, this is done through non-volatile memory, meaning I only need to do it once if my requirements never change. So no, it is volatile memory and it will reset upon removing the power source. So if your power source is constant, then you'll be fine. But if your power source is like a battery and it drains, and it eventually causes the chip to UVLO, then the settings you programmed will be reset. But if it is a constant power source, you can program it with I2C and it will stay as long as the power is valid. Shane asks, if I need a 3.3 volt rail solution, what would you recommend, since the 77812 won't provide that? So it depends. If it's like the only extra rail you need, the 3.3 volt rail, you can, like, we offer quite a few like very small standalone buck regulators that are very simple, and they have a single output and it'll be fixed. And you can just hook one of those up. A subtlety is what your input is. So if you have like an intermediate rail that's 3.3 volts, and you need 3.3 volts out, then you can just, short a wire, honestly, from the input to whatever it is. If your intermediate is like 5 volts, then you should be able to use a buck to get that. Will we get a copy of the presentation? Yeah, you should. I'll have to talk to Hackster about that, but we should have a PDF of the presentation. Maybe we can send it out to you guys like after this is over. We can get that going. Please give more details. Sorry, let me go back to this slide. Also, I'm going to have my email here at the end of the presentation. So if you guys have like in-depth questions, you can just send me an email. And a lot of these things are easier to answer over email because there could be some more information that needs to be talked about. Boris asks, please give more details about the output discharge function. Is the lower MOSFET on the switcher, or is it a separate circuit doing the discharge? So it's actually a resistor that has a switch on it attached to the output cap. So when the output is disabled, that means enable goes low. That discharge function, if it's turned on, will connect that resistor to the output and bring the output down that way. Are the outputs shorted before the enables? No, they're not shorted, but they are held to ground with that resistor if they're on. Can the output discharge be sequenced as well? So if you enable the discharge function, it's going to be basically on at all times. And what that just means is if it's off, the active discharge resistor is connected, and if it's on, the active discharge resistor is disconnected. If you want to like change the timing of that, you'll have to manually do it through I2C, where you can toggle the bit that enables or disables that active discharge resistor. What are some all-in-one modules you recommend over the discrete chip we've gone over today? I don't have any off the top of my head. Maxim does not, like our group doesn't offer all-in-one modules. I believe there might be a few in the company, but I would have to look into what they're made of, basically. I don't have any ideas of modules in mind. Can you show us how to download the CAD files? Yeah, so the CAD files, let's see if I can do this here. So if you go to the Maxim Integrated website, actually if you just type in Maxim 7812, it will bring you to the first link, which is our product landing page. And you can go into the product landing page, you go into design resources, and then you click on EV-Kit here. And it'll take you to the EV-Kit landing page. And under the EV-Kit design resources, you will have, it should be up here. It doesn't look like they're live right now. Huh. They might have been taken down to be changed. I'll definitely look into this for you and get that fixed, but it should be on the, let's check to see if it's not on the product page here. Yeah, sorry. So if you go to the initial thing, just the 77812 landing page, down here you have CAD symbols and footprints for all the devices. The EV-Kit files don't seem to be online. I will look into that for you. Lost questions here. What is the precision of the I2C voltage rail reading? I'm not sure what that's asking. Can you clarify that for me, Michael? Oh, I'm sorry, you guys can't. You guys can't see the screen here. I don't know how to individually switch this. Yeah, okay. Sorry, so all I did was I Googled 77812, Maxim 7812, and on the front page, if you go to design resources, it has your CAD symbol and footprints for the devices here. I guess you couldn't see the efficiency that I shared earlier too. Sorry, I'm new to the Zoom software here. Is it match 0.5% voltage setting? Yeah, so the I squared C is just used. I think what you're asking is setting the voltage through I squared C. Does that give you the accuracy that's listed on the data sheet? And it does. So the accuracy is set by an internal reference and divider. So that's guaranteed inside of the chip. So you don't have to worry about it. The I squared C, all it does is allow you to change that internal setting through software to whatever voltage you want. So all accuracies are guaranteed, if they say that on the data sheet. Chat here. Our FPGA is a good choice for higher voltage applications in the 20 volt, 24 volt, 48 volt range. Does that mean higher voltage, like you need, that's what your source is? Daniel's asking that. I don't know if you can chat here. Yeah, so if you have a 24 or 48 volt source, you can step that down with some nice isolated DC to DC regulators to get them to low voltages to supply the FPGA. 24 volt or 48 volt outputs. So I don't think FPGAs require any rails that require 24 volt or 48 volts. It depends. If you need, the FPGA is really like the end part of your system usually. So you buy an FPGA because you want to do something unique with it. Barry Chiarello asks, either step up from 20 volt or supposed to step down from mains voltage. Yeah, so you're saying you have 24 to 48 volts that's coming from mains, like your Edison supply, to 48. Yeah, so like it depends. So if you have a 48 volt, if you need a 48 volt output, the FPGA is not going to need that. But yeah, it depends on what you want to do with it. Do you need to supply something with it? Oh, FPGAs are not. So FPGAs aren't power supplies. An FPGA is like a high performance, like programmable device. We're talking about powering an FPGA with these power supplies. Sorry, Barry. Are any development boards available to get quicker time to market? So yeah, so the EV kit, like I said, has a. Sorry, I was talking to Daniel. No. Yeah, we're not talking about creating a power supply. So what an FPGA is, a high performance device that you buy that you can program with hardware description language, and you can have it do all sorts of things. But what we're talking about, that FPGA needs power. So we're talking about how to power that FPGA. The FPGA does not generate power. So if you need 24, 48 volts out, that's like an entirely different discussion. Barry, your question is, are development boards available to get quicker time to market? So yeah, we do have the EV kit. You have an EV kit and you do some testing with it, maybe do some sims, you find that it's a good fit for your design. You can take that layout that we've done. If you want a quick time to market, you have the PCB technology and you just use it as it is. But in terms of like, I don't know what the extent of your question is. We don't have like what FPGA is a good fit. It definitely depends on what you want to do with it. So I'm not an FPGA expert. I have pretty minimal exposure to FPGAs. I've only worked with them maybe once in my time as an engineer. Look through Xilinx. They have like so many different FPGAs you can look through. See if there's anything that fits your, yeah. So FPGAs are pretty complicated devices. I recommend looking up like maybe like a Google like how to get started with an FPGA kind of thing. I think it depends on what you want to do, like what's your end goal with your project, and then see if that's a good idea. Whatever the FPGA is going to be a good fit. Yeah, Xilinx is I think there's another company that does them, Altium maybe or something like that. But this presentation is really to say if you have decided that you have an FPGA that you want to use for your project, this is an easy way to power that FPGA. So like I said, if there's any, I think another question just came here. Feel embarrassed in asking this? There's no embarrassing questions. All questions are okay. Power loop, I'm understanding what a power plane is for a PCB. So in a power regulator, you have your input that comes in, and it goes through your IC, your buck regulator does its switching. It generates a lower output voltage. That output voltage, so your current goes from your input through your IC to output to ground back to your input. So it's just like the loop of a circuit. So what I mean by in the context of the PCB is like, you know, you have your output cap, and it has a positive side and a negative side. So the positive side, which is what we're calling the hot loop, is from the positive input through the IC to the positive of the output cap. That's your hot loop. And then it goes down to ground, and then through the ground plane back to the input. That's your circuit. That's how current flows. It's a little bit easier to visualize than it is for me to just describe it to you, but that's kind of what it means. Power, don't feel embarrassed about not understanding this stuff. If you're new to power engineering, it's a pretty complicated field, and there's a lot to be learned. Definitely, like, there are tons of app notes online that you can look up to help you get through these kind of things. No problem. Thanks for joining in. I hope you learned something. And then, like I said, I think, am I sharing the right screen right now? Let me go back to this slide. So there's my email. If you guys have questions, send me an email. I'll try to help you the best I can. And I hope all your designs go well. So I think we're a little over time here, but that's okay. Are there any last minute burning questions, or can we sign off and I'll make sure that we get you guys the presentation in a PDF. No problem, everybody. Maybe Monica, you want to like chime in here and talk about how we can get them the presentation?
Sure. Yeah, I will send out the presentation for everybody. And thanks so much for answering all the questions, Eric. And thanks for joining, everybody.
Yep.
Yeah. All right.
All right.
Have a good
day.
Yeah.
Thank you.